Okay, the other day we looked at motion graphs, particularly displacement versus time. So if you had a displacement versus time graph, you can show displacement as being an S and time on the x-axis as being t, and time is normally on the x-axis there. And if the graph actually just stays at the same position like that and goes across at, say, a position of, say, 3 meters there, because displacement's in meters, changing position there. If that stays at the 3 meter position there, that mark there, has it moved? The answer is no. So in terms of velocity then, we would expect for that whole trip there, the velocity to be 0 there. Okay, so if we look at other displacement graphs that you could get there, versus time, displacement being S, you could get ones where the lines are going up as a straight line, but this time it might be positive, so it might go like that somehow. So if you get one like this here, and it's a change in position, say, of, in the first second it might do a change in position there of, say, 2 meters, and then if you check the second there, it may go up to 4. So if you check this out, in the first second it's travelled 2 meters, so it's actually travelled 2 meters in 1 second. So the velocity, displacement over time, should be 2 meters per second. And if you try the next second from 1 to 2, it's travelled from 2 to 4. So if you check it out, it's still travelled 2 meters because it's gone from 2 meters out to 4 meters. That's the change in position, the displacement. And it's travelled that in 1 second to 2 seconds. That's only worth 1 second period. So again, it's still 2 meters a second. So the velocity here has stayed the same. Now there's a good way of telling that, because for a displacement time graph, the velocity should be the displacement divided by the time. That's the average velocity. It's always distance travelled or displacement over time, and measured in meters per second. But the other thing to bear in mind here is, if you remember your maths there, the slope formula here should be a change in y-axis value, or delta y, or y2 minus y1, divided by x2 minus x1. So that's how you work out a slope. Now, if you can look at what's on the y-axis here, it's actually s is on the y-axis, and time is on the x-axis. So if you look at that, the velocity should be the same as the slope on one of these displacement time graphs. And you should see that's true, because if you look here, the slope here has got a value of 0, because it's not moving, and it's flat basically. So the velocity is 0 because it's not moved, and the slope is 0 because it's got no slope there. It's actually staying at the same height on the y-axis there. If you look at the next one, the slope is staying constant here. Okay, so we expect the velocity to be constant. And in actual fact, if you work out the slope here, it's a y step of 2 over an x step of 1. So the velocity is a constant value of 2 meters a second all the way along. So just remember that the slope will tell you the velocity on any displacement time graph. Okay, now you could get a bit trickier than this and try some others. So if you do some here, what's happening in this one here is, if you were asked to describe this motion here, at the start here it's quite a steep slope, so therefore the velocity is pretty high, and it's also steady. So you could describe this as having a steady high velocity to start with, between 0 and 2 seconds. Here though, between 2 and 4 seconds, the slope is a value of 0. So this has got a constant velocity of 0 because the slope is 0. So it's stopped here for this period of time. There's no change in position. It stays at 20 meters. In the next section, you see it's got a nice steady velocity again because the slope's steady, but this velocity value here is not as high as the other one because it's not as steep. Now you could work these out easy enough. You can look at this and go, the first one's 20 divided by roughly 2 seconds, so that'll be 10 meters a second. And here in 2 seconds you're doing 10 meters, going from 20 to 30, so you're doing 10 meters in 2 seconds. So there it's only 5 meters a second. So you see this one here was 20 and 2, it was 10 meters a second. This one was only 5. So that's the sort of difference you can see there. That's how you can do those. If you look at the next one here, this is a bit trickier because you can see this is a continuously changing line there, which means the slope is continuously changing. So if you were describing this, I'll be talking about a steep slope at the start here with a very high velocity, and as it goes along the slope is going to go down, which means that the actual velocity is going down, and it kind of flattens out to 0 here. So this would be an object that starts with a high velocity and slowly slows down to 0. Okay, and you could show that sort of thing. If you wanted to really calculate the slope at any value, you could draw a line here like this and actually plot a line for each of these points here. So you could actually say, look, if I'm going to do this point here, let's say I want to work out the slope value there, you would go and get a straight line there and try and draw a tangent through there. Not very easy to draw. And I'll just drag it in there. And the tangent at that point there, if I can get this to come in, would actually tell you the slope there. You'd actually go and work out what was the y step here, what was the x step, and you could work out the slope at that point. But obviously the other points here, if you try those out, you can see here that the tangent to the line there is actually like this. And so it's flattened out a bit, so the slope there's not as high, so therefore the speed's not as high. And of course, if you go and try it again in the next bit, it's got even slower because the slope has dropped even slower. You go and try that one there, the slope's kind of dropped out to about that value there, so it's virtually dropped to 0 here at the moment. In fact, you go and play with that, it probably should be on 0. Okay, so that change in velocity there. The slope there at every point will tell you the velocity at every point. So that's a slowing down one. Now you could go even trickier than that with this last one here. The displacement time graph, it goes up there and then it goes down again. So here we're going through the same motion where it's going to start high velocity with a high steep slope, slows down, slows down, slows down, stops here, and then the slope has become negative. This is actually going backwards now because the change in position is going backwards from where it was to start with there. So from this position. So we've got a slope here that's negative and it's getting steeper negative. So this is going to start at a high speed, slow down, stop, reverse in velocity because of reverse direction, go negative and actually speed up in the opposite direction. So this is actually a good graph for someone who throws a ball straight up in the air, where it starts off with a very high speed just as it leaves the hand, slows down due to gravity, stops in midair, just there, and actually then starts to speed up in the reverse direction as it comes back to the hand. Okay, but again, you could work out the slope of each of these. So that's the main thing to keep in mind. Velocity and slope here are going to give you the same value for each section. Okay, thanks.